Hey there, and welcome to the Sleepless Scientist. Tonight, we're embarking on a journey into one of the most profound and elusive concepts humanity has ever pondered: nothingness. What is it really? Can it even exist? And if it can, how did everything we see, touch, and know emerge from it? It's a question that has puzzled thinkers for millennia, from ancient philosophers to modern physicists. It's a quiet mystery, an unfolding contemplation. Before we dive deep, take a moment to settle in. If you're enjoying these explorations, a like and a subscribe truly help us keep uncovering these stories. Now, imagine stepping back in time to the sun-drenched landscapes of ancient Greece. Here, the very idea of nothing began to stir the minds of the earliest philosophers. It wasn't a scientific experiment, but a deep, internal wrestling with logic and existence. One of these thinkers, Parmenides, declared something quite radical around 500 BC. He asserted that nothing could not exist at all. To him, to speak of nothing was to speak of something that wasn't, which was illogical. Existence was all there was, and the void was a mere illusion. Parmenides believed that change itself was an illusion because change implied something coming from nothing or going to nothing. For him, the universe was a single, unchanging, eternal entity. This powerful idea echoed through centuries, shaping how people thought about reality. But not everyone agreed. A generation later, Leucippus and his student Democritus dared to challenge this profound assertion. They looked at the world and saw not a single, unchanging whole, but a universe made of countless tiny, indivisible particles. These particles they called atoms, and if there were atoms, there had to be something between them, something that allowed them to move, to combine, to separate. This something between was their audacious proposal, the void or empty space. The void for them was just as real as the atoms themselves. It was the stage upon which the grand drama of existence unfolded. Without it, atoms couldn't move, change would be impossible. This was a direct philosophical confrontation with Parmenides. Imagine the debates that must have sparked in the agoras of ancient Greece. To accept the void was to accept that nothing could indeed exist, not as an illusion, but as a fundamental component of reality. It was a radical thought, a whisper of a new understanding. Their atomic theory, with its inherent void, offered a powerful way to explain the world's diversity and change. From the smallest grain of sand to the vastness of the cosmos, everything was a rearrangement of atoms in empty space. This wasn't yet science as we know it, with experiments and data. It was philosophy, driven by reason and observation of the everyday world. But it laid crucial groundwork for thinking about the fundamental constituents of reality. The concept of atoms and the void was a bold intellectual leap. It suggested that even in what appears to be solid matter, there is an immense amount of empty space. This idea would fade and resurface many times throughout history. For the atomists, the void wasn't just nothing. It was the necessary canvas for something to exist and interact. It was the silent, unseen partner to matter, allowing for motion, change, and the very fabric of the universe. Their ideas, though revolutionary, would eventually face a formidable opponent whose influence would dominate Western thought for nearly 2 millennia. This intellectual giant was Aristotle. Aristotle, a towering figure in philosophy and early science, found the idea of a void deeply unsettling. He couldn't conceive of truly empty space. It went against his understanding of how the world worked. For Aristotle, nature abhorred a vacuum. This wasn't just a poetic phrase, it was a fundamental principle. If a void existed, he argued, motion within it would be impossible to explain logically. How could something move through nothing? What would resist it? Without resistance, objects would move infinitely fast, which he deemed absurd. So, for Aristotle, a true vacuum simply couldn't exist. Instead, Aristotle proposed that the universe was a plenum, a continuous fullness with no empty spaces. Everything was connected, everything touched something else. This model offered a coherent, albeit different, explanation of reality. Aristotle's influence was immense. His logical, systematic approach to understanding the world became the bedrock of Western thought for over 500 years. His abhorrence of the vacuum became a dogma. During the Middle Ages, few dared to question the established wisdom of Aristotle. The concept of an empty void seemed not only illogical but also, to some, bordered on heresy, suggesting a space where God was not present. Yet even as Aristotle's ideas reigned, practical observations sometimes hinted at mysteries. Water pumps, for instance, could only draw water up to a certain height, around 10 meters, regardless of how powerful they were. This limit puzzled engineers. If nature truly abhorred a vacuum, why couldn't the pump create an infinite vacuum and draw water indefinitely? The explanation remained elusive, often attributed to the strength of the vacuum's abhorrence. These were the first subtle cracks in the Aristotelian edifice. They were not direct challenges to the concept of the void, but rather observations that didn't quite fit the prevailing theoretical framework. The stage was being set slowly for a shift in how humanity approached knowledge. From pure philosophical deduction, the emphasis would begin to move towards empirical evidence and systematic experimentation. The Renaissance brought a resurgence of inquiry, a renewed curiosity about the natural world that wasn't solely bound by ancient texts. Minds began to question, to observe, and to test. By the 17th century, the scientific revolution was gaining momentum. Thinkers like Galileo, though not directly focused on the vacuum, championed observation and mathematical description of nature. His work and that of others created an intellectual climate where long-held beliefs could be scrutinized. The mystery of the water pump's height limit was one such belief ripe for investigation. It was in this era that Evangelista Torricelli, a student of Galileo, proposed a groundbreaking idea. He suggested that the column of water in a pump wasn't being pulled by nature's abhorrence, but pushed by the weight of the air above it. To test this, he used mercury, a much denser liquid than water. If his theory was correct, a column of mercury would rise to a much lower height than water, balancing the same atmospheric pressure. In 1643, Torricelli performed his famous experiment. He filled a glass tube with mercury, inverted it into a basin of mercury, and observed. The mercury column dropped, but only to a height of about 76 centimeters. Crucially, a space formed above the mercury column in the sealed tube. This space, he argued, was a vacuum. It was the first sustained, observable vacuum created and studied by humans, the Torricellian vacuum. This was a profound moment. It wasn't just a philosophical argument, it was a physical demonstration. Nothing could exist not as an abstract concept, but as a measurable, observable phenomenon. But the debate wasn't over. Some still argued that the space above the mercury wasn't truly empty, perhaps filled with invisible vapors or other subtle matter. More proof was needed. Enter Blaise Pascal, a brilliant French mathematician and physicist. Inspired by Torricelli's work, Pascal devised an elegant experiment to definitively prove the existence of atmospheric pressure and, by extension, the vacuum. Pascal reasoned that if atmospheric pressure was indeed pushing the mercury, then that pressure should be less at higher altitudes where there's less air above. This would mean the mercury column should be shorter on a mountaintop. In 1648, Pascal's brother-in-law, Florin Périer, carried a Torricellian barometer up the Puy de Dôme, a mountain in central France. It was a painstaking, difficult ascent, carrying fragile glass instruments. As Périer climbed, he meticulously recorded the height of the mercury column. And just as Pascal predicted, the column steadily dropped as he ascended and rose again on the descent. This experiment provided irrefutable proof. The space above the Mercury was indeed a vacuum, and its height was determined by the weight of the air. Aristotle's abhorrence was finally, empirically, overturned. The whisper of nothing had grown into a clear, measurable reality. It opened a new chapter in scientific understanding, moving from philosophical debate to the tangible world of experiment and observation. This wasn't just about a vacuum, it was about the very nature of space and the bold realization that what appears to be empty can, in fact, be a profound and active part of our universe. But this was just the beginning of understanding nothing. The 17th century had shown us that nothing could indeed exist, a measurable vacuum within a contained space. Yet this was merely a prelude. The deeper question remained, what about the vast, open canvas of the universe itself? The vacuum Torricelli and Pascal found was a space asterisk within asterisk an existing reality. It wasn't the nothing from which everything emerged. That profound riddle still awaited its explorers far beyond Earth's atmosphere. As centuries turned, humanity's gaze shifted from the terrestrial to the cosmic. Powerful new telescopes began to reveal the universe not as a static, unchanging backdrop, but as a dynamic, evolving entity. In the early 20th century, astronomers like Edwin Hubble made a startling discovery. Distant galaxies were not fixed in place, they were moving away from us, and the farther they were, the faster they receded. This observation profoundly changed our understanding of the cosmos. The universe was not static, it was expanding, like a rising loaf of raisin bread where the raisins move further apart as the dough expands. If the universe was expanding, it meant that in the past it must have been smaller, much, much smaller. This simple, logical deduction opened the door to a truly revolutionary idea about our cosmic origins. Enter Georges Lemaître, a Belgian priest and physicist. He was a man of deep faith and rigorous scientific intellect, unafraid to challenge prevailing views. In 1927, Lemaître proposed a radical concept. If we extrapolate the universe's expansion backward in time, all matter and energy must have been concentrated into an incredibly dense, hot point. He called this initial state the primeval atom or cosmic egg. Imagine all the complexity of the universe compressed into a single, infinitesimal point, holding the potential for everything. This primeval atom, Lemaître suggested, then began to expand, not explode in the conventional sense, but to unfurl, creating space and time as it went. This was the genesis of what we now call the Big Bang theory. The idea was met with considerable skepticism. Even Albert Einstein, whose theories of relativity provided the mathematical framework for an expanding universe, initially dismissed Lemaître's interpretation. Einstein famously told Lemaître, "Your calculations are correct, but your physics is abominable." The notion of a universe with a definite beginning was deeply unsettling to many. It challenged the prevailing view of a static, eternal cosmos. Lemaître, however, persevered, presenting his ideas with quiet conviction and strong mathematical arguments. The observational evidence of an expanding universe championed by Hubble gradually lent weight to Lemaître's cosmic narrative. The universe truly did appear to have a beginning. But this raised an even more profound question. If the universe began from a primeval atom, what existed before that? Was there truly a nothing before the Big Bang, or something else entirely? This was not the empty space of Torricelli's tube. This was the nothing from which space, time, matter, and energy themselves originated. A profound philosophical and scientific puzzle. For decades, the Big Bang theory remained a hypothesis, albeit a compelling one. It needed concrete, observational proof, a relic from that primordial moment. The universe, if it began hot and dense, should have left an afterglow, a faint whisper of its fiery birth. But how could one detect something so ancient and diffuse? The answer came not from a grand cosmological experiment, but from an unexpected source, a mundane engineering task in the mid-1960s. At Bell Labs in Holmdel, New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were working with a new horn antenna. Their goal was satellite communication, but they kept encountering a persistent, annoying background noise, a faint hiss that seemed to come from every direction. It was uniform, omnipresent, and utterly baffling. They meticulously checked their equipment, calibrated every component, and even cleared pigeon droppings from the antenna. Every attempt to eliminate the noise failed. It wasn't terrestrial interference, nor was it from the Milky Way. It was something else, something fundamental. Meanwhile, just a few miles away at Princeton University, a team led by Robert Dick and Jim Peebles was theorizing about the very afterglow Lemaitre's theory predicted. They calculated that if the Big Bang had occurred, there should be a faint, uniform microwave radiation permeating the entire universe, a relic from its earliest moments. This radiation would be incredibly cold, just a few degrees above absolute zero, yet it would carry the imprint of the universe's infancy. A chance phone call connected the two groups. Penzias and Wilson described their inexplicable noise, and the Princeton team immediately recognized its significance. The persistent hiss, the annoying background noise, was not interference. It was the cosmic microwave background radiation, the faint echo of the Big Bang itself. This was the smoking gun, the definitive proof that Lemaitre's primeval atom theory, now known as the Big Bang, was indeed the most accurate description of the universe's origin. The universe had begun as an incredibly hot, dense state, and as it expanded and cooled, it left behind this relic radiation, a memory of its first moments. It was like finding the faint warmth of a dying fire, confirming that a roaring blaze had once consumed the entire hearth. The cosmic dawn had been observed. The discovery of the CMB earned Penzias and Wilson the Nobel Prize in 1978, but its true value lay in solidifying our understanding of cosmic history. The universe was not eternal. It had a beginning, a moment when all of existence as we know it sprang forth, but the question of nothing persisted. If the Big Bang was the beginning, what was before it? Was it truly an absolute void, a complete absence of space, time, and even physical laws? Or was it a state so fundamentally different from our current reality that our concepts of nothing and something simply do not apply? This nothing before the Big Bang challenges our very intuition. It is not merely empty space, for space itself emerged from this moment. It is like an artist's canvas, seemingly empty, yet holding the infinite potential for a masterpiece. A canvas that is not merely blank, but pregnant with possibility. The cosmic dawn revealed that everything we observe, from the smallest atom to the grandest galaxy, blossomed from this singular, incomprehensible origin. This transformation from an unknown nothing to the entirety of our universe is perhaps the most profound mystery science has ever encountered. But what if this nothing was not truly empty? What if even the vacuum of space, far from being inert, hums with a hidden energy, a quantum dance that reshapes our understanding of existence itself? The 17th century had revealed a contained vacuum, a measurable absence. Yet the vast, open canvas of the universe still held its secrets. What if this seemingly empty cosmic expanse was not inert, but hummed with a hidden, profound energy? As the 20th century dawned, a revolution in physics began to reshape our understanding of reality itself. Classical mechanics, so robust for the macroscopic world, faltered at the smallest scales. A new paradigm was emerging. Max Planck, a German theoretical physicist, wrestled with a perplexing problem: how objects emit radiation when heated. His calculations kept diverging from experimental observations at certain wavelengths. In a moment of quiet desperation, Planck made a radical assumption. He proposed that energy was not continuous but emitted and absorbed in discrete packets, which he called quanta. This idea, introduced in 1900, was a fundamental departure from classical physics. It was as if a smooth ramp had suddenly been revealed to be a staircase, with each step representing a quantum of energy. Planck himself initially viewed this as a mathematical trick, a desperate measure to make his equations work. Yet, it hinted at an inherent granularity to reality at its most fundamental level. Albert Einstein, just a few years later, would build upon Planck's idea. He used quanta to explain the photoelectric effect, showing that light itself behaved as particles, which we now call photons. These discoveries, along with Niels Bohr's model of electrons orbiting atoms in discrete energy levels, solidified the revolutionary concept of the quantum realm. The universe was far stranger than imagined. As physicists delved deeper into this quantum world, another profound mystery emerged. It concerned the very act of observation and the inherent limits to what we could precisely know. Werner Heisenberg in 1927 articulated this limit with his uncertainty principle. He realized that the act of measuring a particle inevitably disturbs it. For example, to observe an electron's position, one must shine light on it. But light is made of photons, and a photon carries energy which then kicks the electron, changing its momentum. Thus, one could not precisely know both a particle's position and its momentum simultaneously. The more accurately you measured one, the less accurately you knew the other. This wasn't a flaw in our instruments, it was a fundamental property of nature. The quantum world possessed an inherent fuzziness, a probabilistic rather than deterministic reality. If particles themselves were subject to such inherent uncertainty, what did that imply for the empty space they moved through? Could the vacuum truly be a void, a mere absence of everything? Classically, the vacuum was simply nothing, but the quantum realm suggested a deeper, more mysterious reality. This question led to one of the most astonishing predictions in physics. Paul Dirac in the late 1920s sought to combine quantum mechanics with Einstein's special relativity. His elegant equations described the behavior of electrons but yielded an unsettling result. They predicted not only positive energy solutions for electrons but also negative energy solutions. This was problematic. Electrons should always have positive energy. Dirac proposed a radical solution. The vacuum was not empty. Instead, it was filled with an infinite sea of electrons occupying these negative energy states, completely invisible to us. If enough energy was supplied to kick one of these negative energy electrons out of the sea, it would leave behind a hole. This hole would behave like a particle with positive energy and positive charge. Dirac predicted this hole was a new particle, an anti-electron or positron. It would be identical to an electron but with opposite charge. This was the first prediction of antimatter. Just a few years later, in 1932, Carl Anderson observed such a particle in cosmic ray experiments. Dirac's audacious theoretical vacuum, teeming with negative energy, had been vindicated. Dirac's sea was a powerful conceptual model. It showed that the vacuum was not merely empty, but a rich, underlying fabric from which particles could emerge. Over time, this idea evolved into quantum field theory, our most successful framework for describing elementary particles and forces. It paints an even more dynamic picture of empty space. In QFT, the universe is not made of discrete particles in empty space. Instead, it is filled with fundamental fields like the electron field, the photon field, and many others. Particles are simply excitations, tiny ripples or vibrations in these underlying fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. So what then is the vacuum? It is the lowest energy state of all these quantum fields. It is not an absence of everything but the quiescent ground state of all fields. Even at absolute zero, where all thermal motion ceases, these quantum fields still possess a minimum energy, known as zero-point energy. This energy cannot be removed. And because of Heisenberg's uncertainty principle, this quantum vacuum cannot be perfectly still. It must fluctuate, bubbling with activity even in the darkest reaches of space. These fluctuations manifest as virtual particles. Pairs of particles and antiparticles spontaneously pop into existence from the vacuum, only to annihilate each other almost instantaneously. They borrow energy from the vacuum for their fleeting existence, returning it before violating the energy conservation law over longer periods. It's a continuous, invisible dance. This is permitted by the energy-time uncertainty principle, a cousin to Heisenberg's position-momentum uncertainty. It allows for a temporary borrowing of energy as long as it's returned quickly. Imagine the vacuum not as an empty void, but as a boiling, effervescent sea, constantly creating and destroying these ephemeral particles. A quantum foam, vibrant and alive. This isn't just theory. One of the most compelling pieces of evidence for this active vacuum comes from the Casimir effect, first predicted in 1948. If two uncharged, perfectly parallel metal plates are brought incredibly close together in a vacuum, a tiny, measurable attractive force appears between them. The explanation: outside the plates, all wavelengths of virtual particles can pop into existence. But between the plates, only virtual particles whose wavelengths fit the tiny gap can exist. This imbalance creates a net pressure, pushing the plates together. It's a direct, physical manifestation of the vacuum's inherent energy and its invisible, fluctuating contents. The vacuum, therefore, is not nothing in the classical sense. It is a dynamic, energetic medium, a constant wellspring of creation and annihilation, even in the deepest void of space. This invisible dance, this quantum effervescence, is happening everywhere, all the time. It is a profound realization that reshapes our intuition about emptiness and existence. It means that even in the absence of matter, space is teeming with potential, a fundamental activity that underlies the very fabric of our reality. The quantum realm paints a picture of a universe perpetually in motion, even in its quietest corners. But how does this energetic, fluctuating vacuum connect to the grand tapestry of the cosmos? Could this quantum dance, this hidden energy of nothingness, hold the key to understanding the very expansion of the universe and its mysterious dark energy? The quantum realm, with its effervescent vacuum, profoundly altered our perception of emptiness. Yet this intricate dance of virtual particles occurred at the smallest scales. The vast, cosmic canvas, the very fabric of space that stretched between galaxies, still held a deeper, more macroscopic mystery. For centuries, space was often conceived as a static, passive stage upon which the universe's events unfolded. It was the backdrop, the container. But what if space itself was not merely a void, but an active, dynamic participant in the cosmic drama? This radical rethinking began with a quiet revolution in thought, led by one of the most brilliant minds of the 20th century. It demanded a shift from viewing space as empty nothingness to seeing it as a tangible, mutable entity. Albert Einstein, contemplating the nature of gravity, realized that Isaac Newton's description, while remarkably successful, didn't fully capture its essence. Gravity wasn't just a force pulling objects together across empty space. Instead, Einstein proposed something far more profound in his theory of general relativity, published in 1915. He suggested that mass and energy warp the very fabric of space and time around them. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip, a curvature in the sheet. A marble rolled nearby wouldn't be pulled by the bowling ball, it would simply follow the curve in the sheet. This was Einstein's elegant analogy for gravity. Planets orbit the sun not because of a mysterious force, but because the sun's immense mass curves the spacetime around it, and the planets follow these curves. Space, then, was not an inert void. It was an active, dynamic participant, a stage that could be bent, stretched, and twisted by the presence of matter and energy. It was no longer nothing, but a responsive entity. This new understanding of spacetime had profound implications. It meant that the geometry of the universe was not fixed, but could evolve. It set the stage for understanding the universe as a whole. While Einstein's equations hinted at an expanding or contracting universe, he initially added a cosmological constant to force a static solution, reflecting the prevailing belief of his time. The idea of a dynamic universe was too unsettling. However, the universe had other plans. At observatories across the globe, astronomers were meticulously gathering data, looking deep into the night sky, unaware they were about to uncover a truth far stranger than any theory. Among them was Edwin Hubble, working at the Mount Wilson Observatory in California. Using the powerful 100-inch Hooker telescope, he made groundbreaking observations of distant nebulae. Hubble painstakingly measured the distances to these nebulae, proving they were not gas clouds within our own galaxy, but separate island universes, galaxies far beyond the Milky Way. More remarkably, by analyzing the light from these distant galaxies, he noticed a consistent pattern. Their light was redshifted, indicating they were moving away from us. In 1929, Hubble announced his astonishing finding: the farther a galaxy was, the faster it appeared to recede. This wasn't just galaxies moving through space, it was space itself stretching, carrying the galaxies along with it. The universe was not static, it was expanding. This discovery provided the observational evidence that supported Lemaitre's Big Bang theory and forced Einstein to reconsider his cosmological constant, calling it his biggest blunder. The expansion of space was a profound revelation. It meant that the nothingness between celestial bodies was not empty and passive, but an active, stretching medium, constantly growing. For decades, scientists assumed this expansion would gradually slow down, pulled back by the collective gravity of all the matter in the universe. It seemed a logical, intuitive assumption. But in the late 1990s, another surprising discovery shook the foundations of cosmology. Two independent teams of astronomers studying distant supernovae found something entirely unexpected. Supernova, exploding stars, act as standard candles. Their intrinsic brightness allows astronomers to accurately measure their distance. By comparing their observed brightness to their known intrinsic brightness, distances can be calculated. Both teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, observed that distant supernovae were fainter than expected. This meant they were farther away than predicted for a universe whose expansion was slowing down. The implication was staggering. The expansion of the universe was not slowing down, it was accelerating. Something was actively pushing the galaxies apart, overcoming the gravitational pull of all matter. This mysterious force, permeating every inch of empty space, was dubbed dark energy. It accounts for approximately 68% of the universe's total energy density, yet its nature remains one of science's greatest enigmas. Dark energy suggests that even the most profound nothingness, the vacuum of intergalactic space, possesses an inherent, repulsive energy. It's not just a void, it's a source of cosmic propulsion. This concept brings us full circle to the quantum vacuum. Could dark energy be related to the zero-point energy of quantum fields, the constant fizz of virtual particles we explored earlier? The initial calculations, however, presented a colossal problem. When physicists tried to calculate the vacuum energy from quantum field theory, they found a value many orders of magnitude larger than what observations of dark energy suggested. This discrepancy, sometimes called the cosmological constant problem, is one of the biggest challenges in modern physics. It implies a deep misunderstanding of either gravity, quantum mechanics, or both. Despite this puzzle, the evidence for dark energy is robust. It reshapes our entire understanding of the universe's destiny, leading to scenarios of an ever-accelerating, ever-emptying cosmos. The nothing of space is not inert. It bends and warps with matter, stretches and expands over cosmic time, and actively pushes the universe apart with dark energy. It is a dynamic, energetic entity. Imagine the universe as a vast, seemingly calm ocean. From a distance, its surface appears smooth, a serene expanse of nothingness. Yet beneath the surface, unseen currents pull and push. These currents are the gravitational effects of matter bending the ocean's fabric. The ocean itself is expanding, constantly growing larger, carrying distant islands further apart. And permeating this ocean is an invisible, buoyant force, gently yet relentlessly pushing the water outwards, accelerating its expansion. This is the dark energy at play. Furthermore, if we zoom into a single drop of this ocean, we find it's not still. It's teeming with microscopic life, constantly appearing and disappearing, the quantum foam of virtual particles. So, the nothing of space, from the quantum vacuum to the cosmic expanse, is far from empty. It is a complex, energetic, and active participant in the universe's existence. It is the stage, the actor, and perhaps even the director of the cosmic play. The seemingly empty void is a wellspring of potential, constantly shaping and reshaping reality. This understanding challenges our most basic intuitions about emptiness. It transforms nothing from a simple absence into a profound presence, a key to understanding the universe. The universe, born from a singularity, expanding through a dynamic space-time, and propelled by a mysterious dark energy within its very fabric, is a testament to the active nature of nothing. It is a universe where gravity is not a force but a curvature of space-time, where expansion is not just movement but the stretching of the stage itself, where the void is not empty but filled with energy. The journey from ancient philosophical debates about the void to the modern understanding of an expanding, dark energy-filled cosmos reveals a continuous unfolding of discovery, each layer revealing deeper complexity. But what does this profound, energetic nothingness imply for our own existence? How does this active vacuum, this stretching space, and this mysterious dark energy shape our philosophical understanding of being and non-being, of purpose and meaning in a vast, evolving cosmos? The energetic, fluctuating vacuum of space, the stretching fabric of the cosmos, these scientific revelations lead us to a more profound, ancient question. Not just how everything came to be, but why there is anything at all rather than simply nothing. This query, why something rather than nothing, transcends the boundaries of physics. It is a question that has echoed through philosophy and spiritual traditions for millennia, a contemplation of existence itself. From the earliest human civilizations, thinkers have grappled with the idea of a primordial void, a state of absolute non-being from which our vibrant universe somehow emerged. Was it truly empty or merely a different kind of fullness? The scientific journey has shown us that nothing is a far more complex concept than mere absence. It is an active quantum foam, a dynamic spacetime, a source of cosmic energy. How then do these scientific insights resonate with philosophical wisdom? Our exploration now turns from the empirical observations of the laboratory and telescope to the deep, introspective inquiries of the human mind, seeking to understand our place in a universe born from such a mysterious origin. In Eastern philosophies, particularly Buddhism, the concept of emptiness or shunyata offers a profound perspective. It is not a nihilistic void, but rather a radical understanding of reality's interconnectedness. Shunyata suggests that all phenomena are empty of inherent, independent existence. They arise in dependence on other things, constantly changing without a fixed, unchanging essence. This emptiness is thus a fertile ground, not a barren one. It is the potentiality from which everything arises, much like the quantum vacuum, which, far from being inert, constantly gives birth to virtual particles. Imagine a vast, open space in a bustling city. It is empty of buildings, yet it is full of potential, a park, a market, a gathering place. Its emptiness allows for new forms to emerge. This philosophical nothingness is a dynamic absence, enabling change and transformation. It is the very fabric that allows for the dance of existence rather than a static, unyielding solidity. From this perspective, the nothing before the Big Bang might not have been an absolute void, but a state of ultimate potentiality, a cosmic shunyata pregnant with all future possibilities. It implies that existence and non-existence are not separate, opposing forces, but two sides of the same fundamental reality, continuously interplaying. The wisdom here is to embrace this fluidity, to understand that our own identities, like all phenomena, are not fixed but constantly in flux, arising and passing away. This Eastern view offers a calming acceptance of impermanence, finding liberation in the understanding that clinging to fixed notions of self or reality only leads to suffering. It is a profound shift from seeking solid ground to finding peace in the ever-changing tides, a philosophical echo to the quantum realm's ceaseless fluctuations. Meanwhile, in Western thought, particularly in existentialism, the encounter with nothingness often takes a different, more confronting turn. Here, the void is not a source of interconnectedness, but a stark absence. Philosophers like Søren Kierkegaard, Jean-Paul Sartre, and Albert Camus grappled with the implications of a universe without inherent meaning or divine purpose. For them, we are condemned to be free. This freedom is simultaneously a burden. If there is no preordained script, no cosmic purpose, then we are entirely responsible for creating our own meaning in an indifferent universe. The void in this context is the absence of intrinsic value, the silence that greets our deepest questions. It can evoke anxiety, a sense of aimlessness, even despair. The absurdity of existence arises from the conflict between our innate human desire for meaning and the universe's apparent silence to that demand. We seek order in a fundamentally chaotic reality. Yet, even in this confrontation with the void, existentialism finds a powerful affirmation. It is through acknowledging this nothingness that we can truly embrace our freedom and authentic existence. We are the meaning makers. The canvas of nothing invites us to paint our own purpose, to define our values, and to live with courage in the face of ultimate uncertainty. This philosophical journey, both east and west, reveals that nothingness is not a simple concept. It is a mirror reflecting our deepest beliefs about reality, purpose, and our own place within the cosmos. The scientific nothing is teeming with energy, stretching, and expanding. The philosophical nothing is either the ground of all being or the canvas for self-creation. These different interpretations illuminate the profound human need to understand fundamental reality, whether through empirical observation or through deep introspection. Beyond these grand cosmic and philosophical scales, the echoes of nothingness resonate deeply within our personal lives. We experience nothingness in moments of absence and loss. A loved one departs, a dream fades, a cherished possession is lost. These events leave a void, a space where something once vibrated with presence. It is a personal, tangible encounter with absence. The space left behind is not simply empty. It is filled with memories, with the lingering imprint of what was. It shapes us just as the cosmic void shaped the universe. In these moments, we confront our own fragility, the impermanence of all things. The comfort we seek often lies not in filling the void, but in understanding its nature and allowing it to transform us. This personal nothingness mirrors the cosmic mystery. How do we find meaning when faced with the inevitable cycles of creation and dissolution, of presence and absence? It is in these quiet spaces, these personal voids, that resilience is forged. We learn to rebuild, to adapt, to carry the echoes of what was, while embracing the potential of what can be. The human spirit, much like the quantum vacuum, is never truly still. Even in moments of profound absence, there is an underlying hum of activity, a potential for new growth, new understanding. The contemplation of nothingness, whether cosmic or personal, is not an act of despair, but an invitation to a deeper appreciation of existence, of the precious something that we have. It reframes our perspective, highlighting the wonder of a universe that emerged from such a mysterious beginning and the beauty of lives lived in its fleeting, vibrant presence. The intricate interplay between being and non-being, between the something and the nothing, is the fundamental rhythm of the cosmos and of our individual journeys. Our journey through the scientific and philosophical landscapes of nothingness reveals a concept far richer and more active than previously imagined. It is not a blank slate, but a foundational element of reality. From the ancient void to the quantum vacuum, from cosmic expansion to existential contemplation, nothing has consistently challenged our intuition and expanded our understanding. It is the source of all potential, the canvas for all creation, and the silent partner to everything that exists. Its mystery is not a void to be filled, but a depth to be explored. This profound understanding of nothingness reshapes our perception of reality, inviting us to see not just the matter and energy, but the very fabric of space and time as alive with potential. As we stand at the threshold of this holistic view, a final question remains. How does this interwoven tapestry of scientific discovery and philosophical insight culminate in a unified understanding of our universe and our unique place within its grand, evolving story? Our journey through the concept of nothingness has traversed vast landscapes, from the ancient philosophical debates of Parmenides and Democritus to the empirical vacuum of Torricelli's experiments. We've seen how nothing transformed from a forbidden concept to a measurable reality, then to the incomprehensible origin point of our entire cosmos, the Big Bang. The quantum realm further deepened this mystery, revealing that even the deepest vacuum is not truly empty, but a vibrant, effervescent sea of fleeting virtual particles. Then the grand cosmic canvas of space itself unveiled its secrets, a dynamic fabric warped by gravity, stretching with expansion, and propelled by the enigmatic dark energy. From a simple void, our understanding of nothing has blossomed into a dynamic, pregnant possibility, a profound shift in perspective, both scientific and philosophical. It's no longer a mere absence, but an active participant, a fundamental ingredient in the universe's existence and its ongoing evolution. This realization is humbling. The nothing that once seemed so inert now pulses with a hidden energy, shaping galaxies and driving the very destiny of the cosmos. It implies that existence isn't merely a collection of somethings against a backdrop of nothing. Rather, nothing itself is a foundational element, an integral part of the cosmic tapestry. The quantum vacuum, for instance, isn't just empty space between particles. It's the energetic ground state from which particles can spontaneously emerge and disappear. This constant, invisible dance of virtual particles highlights an underlying activity, a ceaseless flux even in what appears to be the most profound stillness. And the dark energy pushing the universe apart is not an external force but an inherent property of space itself. The nothing between galaxies is actively expanding, creating more nothing. This active participation of nothing challenges our everyday intuition. We naturally perceive nothing as an absence, a void to be filled, but the universe suggests otherwise. It implies a profound interconnectedness where presence and absence are not opposites but two sides of the same coin, constantly interacting and giving rise to each other. The universe, then, is not just a collection of stars and galaxies, but an intricate dance between what is and what is not, forever in motion, forever changing. This leads us to embrace the profound mystery that our universe, with all its complexity and beauty, could arise from such quantum potentiality, from this dynamic nothingness. We may never fully grasp the why or the ultimate how. Some questions may simply transcend our current modes of inquiry, residing in the realm of pure wonder. And perhaps that is the most beautiful aspect of this cosmic mystery, to know that there are depths beyond our full comprehension, inviting a sense of awe rather than frustration. The universe, in its very essence, is a testament to the power of potential, the incredible capacity for something to emerge from what we once considered nothing. This contemplation offers a different kind of peace, not the peace of having all answers, but the peace of accepting the grandeur of the unknown. It reminds us that the quest for understanding is endless, and each discovery, no matter how profound, opens doors to even deeper, more beautiful questions. The quantum potentiality from which our universe arose is not a void to be feared, but a wellspring of infinite possibilities, a continuous source of creation. It suggests that the universe is not a static entity, but a dynamic, unfolding story, always in the process of becoming, always revealing new facets of its being. And in this grand, evolving narrative, we, too, are participants. Our consciousness, our capacity for wonder, is a part of this cosmic unfolding. The universe doesn't just contain us. We are, in a very real sense, the universe experiencing itself, contemplating its own origins and nature. This deep connection to the nothingness that birthed everything can be profoundly calming, rooting us in the fundamental processes of existence. It helps us appreciate the intricate dance between presence and absence, much like the essential silence between musical notes that makes the melody beautiful. Imagine a piece of music. The notes are the something, the matter and energy of our universe. But without the silence, the pauses, the nothing between them, there would be no rhythm, no harmony, no meaning. The silence allows the notes to resonate, to be heard, to form a coherent melody. It gives shape and depth to the sound. This is the role of nothingness in our cosmos. It is the canvas, the space, the potentiality that allows for the vibrant, complex symphony of existence to unfold in all its glory. Every star, every galaxy, every breath we take is part of this cosmic composition, made possible by the underlying nothing that hums with potential. This perspective allows us to find peace not in the absence of mystery, but in its very presence. It invites a deeper reverence for the universe's inherent wonder. The journey has shown us that nothing is far from empty. It is pregnant with possibility, a dynamic wellspring from which everything we know and love has emerged. It is the silent partner to all creation, the quiet strength that underpins the vibrant existence of the cosmos. And in understanding this, we find a profound sense of belonging, a connection to the very origins of space, time, and consciousness itself. This scientific and philosophical contemplation of nothingness culminates not in a definitive answer, but in a deeper, more expansive appreciation of existence. It is a journey that began with simple questions and has led us to the edge of the knowable, inviting us to marvel at the sheer fact that anything exists at all. The universe, in its grand design, whispers of a beginning from profound potential, an ongoing dance of creation and dissolution, a tapestry woven with both presence and absence. And as we reflect on this cosmic story, we find a quiet resonance within ourselves, a mirroring of the universe's own dynamic nature. The sleepless scientist, ceaselessly pondering the mysteries of the cosmos, ultimately finds solace not in complete understanding, but in the beauty of the enduring questions. And so, as the moon climbs high and the stars continue their silent, ancient dance, may you find peace in the vast, wondrous tapestry of existence. Sleep well.